Please pay attention of what we are discussing here. I'm going to define what's an acid. An acid contains hydrogen atoms and it dissolves in water to form hydrogen ions. What's an acid? An acid means it's a substance that dissolves in water. When it dissolves in water, it donates a hydrogen ion. Everybody remembers that, right? So, for example, HCl is considered to be an acid because when it dissolves in water, AQ, everybody noticed what AQ means, right? The AQ is, AQ means it is aqueous solution. Aqueous means if something dissolves in water. So, we have a hydrogen ion is donated here. A base means it's a hydroxide. A base contains a hydroxide and dissolves in water. It contributes OH ion. That's a base. For example, we have NaOH. When sodium hydroxide dissolves in water, it increases the concentration of OH ion. Okay? So in that regard, base is always coming from the adding of more OH ion in water solution. Okay? This definition is called the Arrhenius definitions of acid and bases. But sometimes this definition is also considered to be as limited at some point because even some chemists consider this as inaccurate. The reason why further investigation have shown that you don't have hydrogen ion per se in water. When hydrochloric acid, for example, dissolves in water, there is no like H plus ion, but rather what you can see is that a hydronium ion, which is H3O plus. Okay, so this is not perfect definition for an acid because there is H3O plus because you have water there, and one hydrogen ion is interacted with the water molecule here and forms H3O plus. We don't see the H plus as a single ion. So the Arrhenius definition is somehow limited or sometimes is considered to be as inaccurate in this context. So they have another definition, which is a Bronsted-Lowry acids and bases definition. A Bronsted-Lowry acids and bases definition. A Bronsted-Lowry acid and base definition says that an acid is simply a proton donor. Okay? If a substance can donate a proton, which is a proton is hydrogen ion, is said to be an acid. A Bronsted-Lowry base is a proton acceptor or hydrogen ion acceptor. This is somehow accepted by the scientific community, and it is more accepted as definitions of an acid or a base. For example, you have a reaction here, hydrochloric acid, react with water, you will have H3O plus and chloride minus. Okay? In this regard, hydrochloric acid is a Bronsted-Lowry acid because it contributes or it donates hydrogen ions to water. Okay? And water here is considered to be as a Bronsted-Lowry base. The reason why? Because water accepts hydrogen ion from the acid. Okay, so this is a Bronsted-Lowry base, and this is a Bronsted-Lowry acid. So we're not defining acid as a substance that is always has contributing hydrogen ion, which is true, but it is very limited. A base is a substance that is contributing OH ion in a solution. It's also true, but it's also very limited. So the big definition, the big picture of acid and base is if any substance accepts base, accepts hydrogen, it is a Bronsted-Lowry base. If a substance accepts hydrogen, it gives hydrogen, it's called a Bronsted-Lowry acid. Okay? These are some examples of a Bronsted-Lowry acids. In fact, again, you have to always think about that. If a substance is an acid, you think it needs to have hydrogen ions. That is the criteria. Okay? It has to have an acid. So for example, here we have HCl, we have HBr, we have HNO3. What do they have in common? All these have hydrogen ions, right? So they are an acid. Okay, they are an acid. We have 2 hydrogen ion. We have 1 hydrogen ion here. Also, it's important to know the number of hydrogen ions tells you what type of acids you have. You have a monoprotic acid and a diprotic acid. Okay, monoprotic acid is an acid that have 1 hydrogen ions. These are examples of monoprotic acids, for example, like HCl, HBr, HNO3. Since they are donates 1 hydrogen ion, we call them what? Monoprotics, right? Diprotic acids, like sulfuric acid. Okay? Can you give me another example of diprotic acid? An acid that has 2 hydrogen ion. Wait. Huh? Hydrochloric?
No.
Hydrochloric acid is a monoprotic acid. The diprotic acid, it needs to have 2 hydrogen ion. How about carbonic acid? What is the formula for carbonic acid? Kathy, what's the formula for carbonic acid? Carbonic acid comes from carbonate, right?
Yeah.
Which is?
CO3.
And the formula is going to be?
HCO3 minus the
No. Carbonic acid is going to be? H2CO3. H2CO3.
Oh, H.
Okay. We have an acid. If you have more than 2 hydrogen ions, ammonia is not an acid. Ammonia is not an acid. Yeah. Ammonia is what? Ammonia is a base. I'm sorry?
What was H2CO3?
H2CO3 is a carbonic acid, and it's called a diprotic acid. Yeah. H2CO3 is because it has 2 hydrogen ion in it, right? It's an acid, but it's a diprotic acid, right? If I have HNO3, it's an acid, it is a monoprotic acid because it has 1 hydrogen ion. Okay? If I have H3PO4, what's the name of this acid? No. H3PO4 is going to be, it comes from phosphates. Any acids from phosphates? Come on, this is going to be our last class in chemistry. Still, you don't know the name? Yes,
Is
yes.
it phosphoric acid?
I'm sorry?
Phosphoric acid?
Exactly. It's phosphoric acid. Phosphoric acid. How do we know that's phosphoric acid? It comes from phosphate. Anytime when you name acids, if you have phosphate, you use the suffix IC. So from phosphate you have phosphoric, right? If you have carbonate, you have carbonic acid. If you have sulfate, what is the formula for sulfate? Sulfuric. Sulfate is SO4 2 minus. Then the acids, the corresponding acids is going to be the corresponding acid made from sulfate ion. You have sulfate, SO4 2 minus, and you add how many hydrogen? 2 hydrogen plus, right? What do you get? H2SO4. And what do you call this? Sulfuric acid. Always ATE have to have a suffix for of IC. Okay. For example, I have chlorate or bromate. What is the formula for chlorate? Chlorate is made from chlorine, Cl. No, chlorate is ClO3. Chlorate, not chloride, chlorate. ClO3. Okay?
Oh, I thought you said.
Chlorate is, you add 1 hydrogen ion. Why I have to add 1 hydrogen ion? Because the net charge is to cancel this, right? So 1 plus and 1 minus, it gives me 0. It's going to be HClO3. Okay? HClO3. So it is an acid, right? What kind of acid it is? Chloric acid. chloric. Every time when you name acids, the ATE has to be changed into what? IC. And based on the number of hydrogen atoms you have, 1 atom or 2 atoms, you can also classify them as monoprotic acid and what? Diprotic acid. Maybe polyprotic acid if you have more than 1. Okay? Over here, a Bronsted-Lowry acid, as I have said, is a proton or hydrogen donor. A Bronsted-Lowry base is a proton or hydrogen acceptor. So we have hydrochloric acid and water. The product will be H3O and chloride. The hydrochloric acid is a Bronsted-Lowry acid. The reason why? It donates a proton. It donates a hydrogen ion to the solvent water, to water here. A water is considered to be as a Bronsted-Lowry base because it accepts hydrogen ion from the hydrochloric acid.
I thought water was not considered acidic or base. I thought it was just the normal.
Yes, yes, but you see, it's confusion here. Water is, if you're talking about a pure water, it's considered as is neither acidic or basic. But if it's not pure, you can't say it can be acting as an acid or it can be acting as a base.
So you're saying whenever you have pure water and you add something to it, you either make it acidic
Yes,
or basic?
yes,
Okay.
depending on what concentration you add. If you add more of the acidic solution, water is acting as an acid. Actually, we're going to come to that definition. So, you see, so from now on, maybe in the future, if someone asks you, what's the definitions of an acid? Simply, you can trick them by saying, no, an acid is a substance that provides hydrogen ion in a solution. That gives you hydrogen ion in a solution, or a basic substance that provides you OH ion in a solution. But if you want to go deep a little bit, if you want to go details, when acid dissolves in water, you don't see hydrogen ion per se. You don't see that hydrogen ion. There is no any hydrogen ion. The experimental result doesn't show you hydrogen ion. What it shows you is that hydrogen ion make a conjugate with water molecule. Instead of H2O, you have H3O. There's no acid, there's no H plus. Okay? So what they preferred is they preferred this definition. Acid means whatever acid is, as far as if the substance gives away proton. A base is, it doesn't necessarily have OH. It doesn't necessarily have OH, like water can be a base. As far as it accepts a proton. It accepts a proton here, so it is considered to be as a base. So this is a more acceptable definition. Bronsted-Lowry acids and Bronsted-Lowry base is a more acceptable definition. Okay.
So, Professor, is
Yes.
tap water considered pure water?
Now, pure water means H2O. Tap water is not a pure water. A pure water means you have only 2 atoms of hydrogen and 1 atom of oxygen. In tap water, you have a lot of trace elements like sodium ion, chloride ion, potassium ion.
So tap water is considered a solution?
Water is considered to be as a universal solvent. Okay, so water always have some elements in it. So in tap water is always, there are some nutritional values too. Okay.
Okay, I'm asking this because on the test, you remember the first question is like
Exactly the same thing. I know what you're talking about.
right? So is water the answer? Like is water a solution? Because
Water is a solution, yes. Water is a solvent. Water is a media. Water is a solvent. Water forms a solution.
that was my question, right? Please, can you give me the first question of the test to us? Please, sorry, thank you.
Well,
It's not a solution.
I don't have a real reason.
You have it. Right?
Which is the following, which is not an example of a solution. Okay, a dental filling, chicken noodle soup, gathering, tap water, which one do you think?
Tap water. Because there is no solvent, there is no solute.
I put something else because I'm thinking tap water has chlorine. I know, right? So,
I mean,
use gas.
I use gas too.
You said you guess.
No, it's
Chicken
not.
noodle soup sounded good to me.
Hot water is like,
Not, he said not.
mostly is solvent, but
Chicken
solution
noodle
is two or more
Yeah.
components.
Okay, well, you have to
Like, if you
understand
think about
that
a
in tap
toothpick,
water, you
You gotta
have
combine
serious
stuff to
particles.
make the
You
film.
have chlorine, you have potassium, you have sodium, you have all nutritional values. Okay? Water
Chicken noodle soup.
is as a pure solvent.
Chicken noodle soup, chicken,
It has
the
a
mixture is like the,
Huh?
It has a mixture.
solute. Yeah, it's mixture.
But it's not a solution or a solvent, it's a food.
No, it's
It's a
solution.
mixture of
It's a
Okay.
mixture.
things.
I'm going to give you the
It's
right
so-
answer next week, okay?
And so is a tooth filling. A tooth filling is a mixture.
Exactly, which is
So
also.
it had been the
solution.
gases.
So I say this very good.
Yes.
The gasoline will be the best answer. Yeah.
Yes.
I thought gasoline had
It's a mixture, it's a solution, a solution of like one or more compounds, two or more compounds.
Okay? So,
Right.
tap water, we need to consider here for bronze loaded bases. Lone pair makes this neutral compounds a base as well. What it means is that, see, maybe, I think you mentioned this ammonium or something earlier, I remember. Ammonia is considered to be as a base. This is also considered to be as a base, water. We have to know, do you remember about the Lewis structure we have done? Lewis structure, have you noticed when we draw Lewis structure, I don't know, maybe chapter 5 or chapter 6? Yes, no? Lewis structure, when you want to Lewis structure is, for example, we have ammonia, right? What is Lewis structure? L-E-W-I-S, and Lewis structure tells you. It tells you how the electrons are distributed around the central atoms. Okay? So, ammonia, for example, this NH3 is considered to be as a basic solution. Okay? According to the Bronsted law in bases, as far as it accepts hydrogen ion, it's a base, right? But that's not the only reason that we consider this as a base, because bases also need to have a known pair of electrons in order to accept something. You accept something, you just, how do you accept them? You need to have some kinds of interaction. There should be a molecule, that will be, there should be electrons, free electrons or lone pair electrons that can interact and to form a compound. Okay? So a little bit we need to know about, besides having the OH. The OH is without any question. Any substance that has OH is assumed to be what? It's hydroxide. It's a base, right? But like ammonia or water in this regard is considered to be as a base because they have a lone pair of electrons. If you know the structure of ammonia, you will have something like this. And two lone pairs are here. This is a structure. This is what we call it Lewis structure. Okay? How do we draw Lewis structure? How do we draw them? I will take this as a review class, maybe. We take the central atom, always. The first atom is considered to be a central atom. And we have to know how many electrons we have. Say, for example, what is the valence electron for nitrogen? 5. Hydrogen is 1. The valence electron.
Oh,
the valence. You know what valence electrons are, right?
Yes.
The electrons that are located, that are in the outermost shell of the last shell of an atom. So basically, so we have 3 plus 5. We have 8. Right? We have 8 valence electrons. So we use each of these 8 valence electrons to form a bond, to form a structure. And the way that we form a bond, because the electrons are like charges, they are repelling each other, we're not going to regroup them in one, assuming that they are repelling, there's a repulsion force, so they're like far away from each other. That's how the structure looks like this, like a trigonal, pyramidal, or a tetrahedral, something like that. So now we have 2, 4, 6, 8, because we have 8. See, Lewis structure is actually telling me that how the valence electrons are distributed around the central atom. That's how loose structure is. Okay, so now let's go back with the idea here. Because we have a lone pair of electrons, this considers to be as a base. Does it make sense? Yeah, this considers to be as a base. Why? Because by the definition here, the Bronsted-Lowry base, what is the definition of Bronsted-Lowry base? It accepts hydrogen ion. So, if it accepts hydrogen ion, there must be a molecular interaction. To have a molecular interaction, there must be what? A lone pair of electrons. Okay? So, these lone pair of electrons are free to interact with any of the hydrogen ions comes from the other corner, from the other side. So they are ready, they have room, in other words. You see? So sometimes, you know, you may be tricked. Oh, NH3, if I look NH3, there is no OH there. How can you say that NH3 is a base? Because NH3 has a lone pair of electrons. How do I know NH3 has a lone pair electron? I have to draw the loose structure. Okay? I have to go back with the loose structure.
So if that was,
You see,
Am I
like,
okay,
yeah,
go ahead.
yes. What I'm going to do, maybe on the test, I know it might be confusion. I just write a formula and I'll say, is it a base or is it an acid? It's very hard to say unless you don't have H or you don't have OH. Okay, if you have H, most likely the compound is an acid, right? If you have OH, most likely 90% the compound is a base, right? But if you have NH3, like this lone pair of electrons, it is also acting as a base because it can accept hydrogen ion. This is also acting as a base because we have a lone pair of electrons here. Yes?
so if they didn't actually weren't able to accept it, then it'd be an acid? If it didn't have like the lone electrons?
I wouldn't say that. I wouldn't say that. For an acid, I'll be very much specific because if they don't have a lone pair of electrons, they can be something else. For an acid, it has to have a hydrogen ion. It has to have hydrogen ion. If I tell you that, you know, that will be very ambiguous. Sodium chloride doesn't have a lone pair of electrons. NaCl, is it an acid? No. NaCl, sodium chloride, salt, common salt. It's neither. It is neutral. See? But there is no lone pair of electrons there. So, Kila, that definition doesn't work for an acid. So I will state an acid is a substance that has hydrogen ions in it. Okay?
Okay, but a base has to be able to accept, right?
Accept, yeah, has to be able to accept
Okay.
because it is a donor, it is acceptor,
Right.
a proton acceptor.
Okay.
So criteria, one of the criteria is that either it has OH or it has a lone pair of electrons.
Okay.
So there's like there's like a space or orbital or a room for whichever hydrogen comes from the other corner. Can't have a space there.
Okay, Professor, another
Yeah.
thing is, would it be right to say all acids start with hydrogen? Because hydrochloric acid starts with hydrogen.
Yes. But an acid, yes.
So hydrogen
Sulfuric acid.
Sulfuric acid
It's an
starts
acid,
with
yes.
H,
Yes.
and phosphoric acid
It's an
also
acid.
starts with H. So is it right to say all acids start with H?
Oh.
Exception of water, because water is also H.
Well, no. Again, for example, I have this. Do you know what is this? It's a common acid used in vinegar. Acetic acid. Acetic acid, acetic acid, yes. Acetic acid makes from acetate ion and hydrogen ion. Now, no, acetate ion is CH3COO minus and H plus. H is at the end. It's an acid.
Okay.
Okay, so you know, I'm not like trying to make your case invalid, but it is like it's not. It doesn't work all the time.
Oh, okay.
It doesn't work all the time.
I understand. You did the OH3, you said it was 8, but then it's 2.
Okay, here A base must contain a lone pair of electrons that can be used to form a new bond to the proton. This is the same thing I explained. A base, this is a base. Pair of electrons form a new bond, right? Why? This is a Bronsted-Lowry base. It accepts hydrogen ion, right? Maybe from water here, right? Since it accepts hydrogen ion, it accepts one hydrogen ion from here. And then because of this lone pair of electrons, do you understand? This lone pair of electrons, it can accept and form a molecule, which is ammonium here. It's ammonium ion, NH4 ion. There is a room to accept one hydrogen here. Okay, so this is a base. By this definition, by the Bronsted-Lowry base definition. Water, in this case, is what? It is an acid. You don't believe that, but it's an acid, according to this definition. Why? What is the definition? So what is the new definition of an acid? An acid is a substance that donates hydrogen ion. I don't care what it is, but as far as it donates hydrogen ion, it's an acid. So we have Bronsted-Lowry base, we have Bronsted-Lowry acid here.
So the product is what?
The product is ammonium ion and OH ion.
So
Did you just
Why
say that
did you
H2O
say
is
base?
base? Right here it says
Oh,
H2O is base because it accepts
Oh, H.
proton from HCl.
What's that? What did you say?
It says H2O is a base because it accepts a proton from HCl, but now it can act like an acid or a base?
H2 is not a base. H2 is an acid.
It says right here that it accepts protons from HCl, so it's a base.
Yeah, I guess when it
Is it
combines with
conjugated?
HCl, it's a base, but when it combines with
Reactive
No,
side
it's
and
not.
product side.
Okay, let
That's
me
the problem.
maybe explain a little bit here that can give us a full picture here. Okay, let's put it
So,
here.
I mean, can water be a base or
An acid. Yes,
right?
ma'am.
Okay.
Yes.
It just depends on what it's
combining
combining with?
Yeah.
Right.
Yes.
So how do you know whether it's an acid or a base?
Okay, we have a reaction here. What's this reaction here, right? This reaction maybe explain a little bit what's an acid or a base. Now, this is an acid here, right? Because it has hydrogen ion here. We have a base here. A base, not like OH, but since a base, we have a lone pair of electrons. An acid, loss of hydrogen ion, and it become A minus, right?
Mm-hmm.
It become A minus. Now, this case, it's going to be a conjugate base. A conjugate base is formed from the acid that already lost a hydrogen ion. Okay, now we have a base here.
I have a question.
Let me finish. Okay, let me give you, let me
Because I don't get the A-B thing. I was wondering if you've
Okay,
actually put
go
that
ahead.
in a formula, so I
Okay.
can understand it.
Go ahead, what's your question?
Well, I mean, I just want to know if you could put like sodium in there or something instead of A and B, because that's just confusing.
Okay. Let's see. I would put HCl and I'll put the base maybe okay, maybe water. Okay. Now, what do I get here? I get Cl minus and H3O plus.
So I can understand that more.
Okay, so this is an acid. This acid lost one electron, lost hydrogen ion here, right? It becomes a chloride minus. So this guy is going to be conjugate base. Okay, this is a base. So water. This is a base. It accepts the hydrogen ion here from the acid. From the acid, this becomes a conjugate acid.
Okay.
But this is a base. That's what it is. You have an acid, you have a base. When acid loses a hydrogen ion, it becomes the corresponding substance is become conjugate base. This is a base. It gains one hydrogen from here. The one that's lost, the amount of electrons, the amount of hydrogen lost has to be gained by the second substance to balance that.
Changes.
So from the base, because it gains of hydrogen ion, the one that's lost, it becomes a conjugate acid. It becomes conjugate acid. In this case, the conjugate acid is H3O plus, the conjugate base is chloride. The conjugate base is born from the acid, okay? The conjugate acid is born from the base, okay? Okay. Okay, yeah, let's see. You know, sometimes if you have acids, you have strong acids, okay? You have a strong acid, you have a strong base. What is a strong acid? A strong base means when a covalent acid dissolves in water, the proton transfer that forms H3O is called dissociation. A substance is strong or weak depending on how the hydrogen ion is dissociated. There is a dissociation, there is a complete dissociation and there is a partial dissociation. For example, this is experimental proven. Yesterday, you guys did experiments with hydrochloric acid. I don't know, maybe hydrochloric acid. You see the intensity of the light, right? The intensity of the light in some cases was very, very bright, very strong. When you add some substances, the others are weak. The light was weak, right? The bulb. When you inject in some of the sucrose or I don't know what, you never saw light. What is the reason for that? There is no dissociation of ions. Sometimes you see a weak bulb, a weak light, right? Sometimes you see very intensive lights, right? What does that tell you? The higher the ions, there is a strong electrolytes. Strong electrolytes is actually comes from complete dissociation of the ions. Okay, so dissociation is different from dissolving of the ions. That's why a lot of people get confused. Sugar dissolves in water completely, but sugar is not dissociated in water. Dissociation means forming ions, forming a positively and a negatively charged ions. Now, in this case, hydrochloric acid is a strong acid because it dissolves 100%. It is a forward reaction, you see. This reaction, forward reaction, means there is no backward. That means all HCl is completely dissociated. A single reaction arrow is used because the product is greatly favored at equilibrium. We have products, we don't have reactants, right? Which one is an acid? Hydrochloric acid, right? Why is hydrochloric acid is an acid? Because it donates hydrogen ion, right? Which one is a base? Pronicillary base? Water. 2 H3O, right? And what is H3O? Is it a conjugate acid or a conjugate base? A conjugate acid.
Oh yeah,
A conjugate acid. What is Cl minus? A conjugate base. Now, yes. Okay, it's clear? Okay. Now, we also need to know about common strong acids. You will be asked this on the exam. Hydrogen iodide, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid. These are common strong acids. What is the criteria? The criteria is that there is a complete dissociation there, okay? Now, mostly, acids of halogen families are strong acids. Okay, I'm not saying this like 100%, but I can tell you most of the halogen acids are strong acids. Unfortunately though, there are exceptions. Like HF, hydrofluoric acid, is not a strong acid. That means it's not completely dissociated. Fluorine has a higher electronegativity, is a powerful electronegativity, so it's very hard to break up the bond in a water molecule. So hydrofluoric acid is considered to be as a weak electrolyte. There's no complete
Is
dissociation,
that
but
because it won't dissolve?
it dissolves. It
But
dissolves,
not
but it's not
completely.
completely dissociated.
Right.
It not completely turns into ions. Okay, that's what it means.
Okay.
So these are, I want you to maybe pay attention or just look these compounds, the hydrogen iodides, hydrogen bromide, hydrochloric acid, sulfuric acid and nitric acid are pretty much strong acids. They are completely dissociated in water.
Is sulfuric acid the same thing as tetraoxosulfate?
Yeah, but you know, the common name for sulfuric acid is we use H2SO4 as sulfuric acid. Okay, we use sulfuric acid. Like we have phosphoric acid, it's a weak acid. Like HF is a weak acid. Organic acids are weak acids, like acetic acid, like this vinegar. These are also weak acids. They are acids, but they are weak acids. So most of the strong acids are acids of halogen families, with the exception of HF. With the exception of HF. Okay? Write that down. Here, it's also here. Weak acid dissolves in water, only a small fraction of the acids dissociates into what? Ions. Dissociate into ions. Again, dissociation is a very key word here. Unequal reaction arrows are used because the reactants are usually favored at equilibrium. Because you remember on strong acids we have only one side, one arrow, but here we have two arrows. That means the products are getting together and back to the original molecule. So what we can see from here is that you don't have only ions, you also have molecules. There is a forward reaction, there is a backward reaction. So in the solution you have molecules and ions together. Molecules and ions together. So these are the common weak acids. Phosphoric acid, what's HF? Hydrofluoric acid. Carbonic acid is a weak acid. And hydrogen cyanide is a weak acid, okay? So, I mean, there are not too many numbers. I would suggest to remember the names. Okay? When a strong base dissolves in water, there is dissociation, 100% dissociation. That means sodium hydroxide dissolves in water, sodium ion and OH ion. Most of common strong bases are sodium hydroxide and potassium hydroxide. Pretty much hydroxides of alkali metals. You remember where the alkali metals are? What are the alkali metals? Lithium, sodium, potassium.
Oh no, no.
What is rubidium? Look. Lithium, sodium, potassium, rubidium, cesium, francium, okay? These are the alkali metals. Most of the alkali metals, hydroxides, are strong bases, okay? In this case, they just prefer to have sodium and potassium, but just for your information, alkali metal hydroxides are strong bases. In other words, when they mix, when they dissolve in water, there is what? 100% dissociation into ions, okay? And it's only forward reaction. There is no backward reaction. A weak base dissolves in water, only a small fraction of the base dissociated, not 100%, maybe 50% or maybe 40%. Okay? So you have a gas and a molecule. Like ammonia is considered to be as a weak base. When it is not completely dissociated, because the ammonium ion and the hydroxide ion coming here and they form a basic solution. Okay? So in this case, Kayla, I have a question, right?
Yeah.
Okay, can I please? Okay, go ahead.
No, it's okay.
Go ahead.
Oh, I was just wondering, how would you, like with these formulas, determine whether they've actually dissolved all the way? Is it because they're still the same letters and only like one dissolved, or you get what I mean?
What do you mean? Like, what do you mean?
Like, how can you tell the difference between a strong base dissolved to a weak base dissolved by these?
Well, actually, this is experimentally determined values. Okay, this is not something like I have to see, but this is already done. It's experimentally proven, okay? If you have any alkali metals, any of the alkali families with water, they completely dissociated. Why? Because alkali metals are naturally very reactive. They can react with water and they form hydroxide. They can easily be dissolved. Well, that is the nature of the alkali metals. If you take another metal, group 3 or transition metal, they are not that much active with water.
Okay, so the alkalines are the stronger ones.
The
whereas
alkalis are
rest
the
of them
strongest
are-
one. Yes,
Okay.
yes. The alkalis are the strongest one.
You said the alkalines are the strongest one, except what?
Well, except what? Except hydrogen, for example. I mean, I can give you an example for it here. For example, even the alkaline earth metals like calcium, maybe calcium, strontium, barium, radium, they are very active too. They can.
And boron are not.
No. Yeah, the top one are no. Okay, the top one are no. Now let me go back one more thing here. Now it might be a tricky question here. Which one is that? Bronsted lowry and acid, bronsted basic and acid from here. Bronsted base and bronsted acid here.
The base is.
Okay, ammonia.
The base is the.
The base-
Ammonia
And that's
absorbs hydrogen here. So ammonia is what?
The acid.
It's the acid.
Ammonia we say is base.
Ammonia absorbs hydrogen here. It's
Oh,
base.
ammonia is
in
base,
H4,
we say ammonia
right?
base.
Right, so
Ammonia is a base here.
Yes.
Yes,
Okay.
what is the acid?
Ammonia is a base. But this guy right here is
acidic.
a conjugate acid or a base.
Conjugate acid.
Conjugate acid.
A conjugate acid. Water, in this case, is what?
Acid.
Water is considered to be as an acid here. Because water gives away hydrogen ion.
I say conjugate.
Water gives away hydrogen ion, right?
Right,
But over here, if this is an acid, OH is what?
conjugate base.
A conjugate base. It's a conjugate base. So try to relate that fact, okay? Now, you see, because, water is a neutral, but no, depending on where you are, depending on the reaction, water can be an acid.
Can we do the same thing for the top one?
Yes, from sodium hydroxide and the water, okay? What do you want to do? What is sodium hydroxide with sodium? What is the sodium does here?
Base.
Gives away this.
The sodium is a base, right? Because it provides OH ion. Water, what does water does?
Acid.
Water is an acid, it provides hydrogen ion. So the corresponding compound is a conjugate base. Okay? This is a conjugate acid. So try to relate that fact. Okay, this is, I already said this. A strong base is always completely dissociated. A weak base is partially dissociated, or there are undissociated base of ammonia. Here, if we have pure water contains low concentration of ions, that means H3O ions and OH ions. So, we have a concentration value here. If you have a pure water, the concentration of H3O, which is the acidic medium, and the OH, the basic media, are the same. Then, when you measure their concentration at room temperature, their concentration is 1 × 10⁻⁷ molarity. That is experimentally determined value. The pure water means a water that have equal concentration of the hydrogen ion and the OH ion. But we don't have hydrogen ion per se, but we have H3O ions, right? H3O, because we know that there's no hydrogen ion. The hydrogen ion has to react with H2O, H plus H2O together, it forms H3O. So pure water means what? How do you define pure water in chemistry? No.
H2O.
No. What is that?
H2O.
It's the ones that have the same concentration of H3O and OH. A pure water means a water that has equal concentration of H3O and OH. Okay? Because when water decomposed, H2O, when it decomposed, it turns into H plus and OH minus, right? when it is broken down, right? H is refers to acidic. OH refers to base, right? So if you have the concentration of H is more, it is acidic, right? Water can be acidic. If you have the concentration of OH more, it is basic. See, water can be both. Now, what is pure water then? Pure water means if you have the same H and the same OH, and it is 1 times 10 to the power of minus 7 molarity. That is what pure water is defined.
Is that because they cancel each other out?
No, they have the same amount. Okay. This actually, when you do the logarithm of this, you know, the pH of water is 7. Okay, 7 because pH is minus logarithm of concentration of either solution, right? So logarithm of 10 minus 7, concentration of H, right? So if you remember the logarithm of 10 to 10 to the power of minus 7, if you have logarithm of 10 to 10 to the exponential A, right? It is the same as A times log 2 the base 10 to 10, I forgot how it is, but that's how it is, right? This gives you 1, okay? 1 times 7 is what? 7. So 7, you remember 7, right? 7 comes from here. This is what 7 is, okay? So now anything over 7 is going to be basic. Anything below 7 is going to be acidic. When do you get 7? When the concentration of H ion and OH ion have to be the same. So adding a little bit.
So 7 is pure water then? That would be
The
the
pH, yeah,
definition?
well, 2 ways. The pH 7 is pure water, but the concentration of H has to be 10 to the power of minus 7. And the concentration of H3O, I mean the concentration of H, hydrogen ion, has to be 10 to the power of minus 7 M. The concentration of OH is also has to be 10 to the power of minus 7 in order to define it is pure water. In terms of the pH paper, in terms of the pH measurement, it has to be 7. Okay? So multiplying these concentrations together, it gives you the ion product constant. So that means the constant value means if you multiply H3O with OH, you get what we call the ion product constant here. And then, you know, that gives you 14. You know, 14 is the maximum number. 10 to the power of 7 minus 10 to the power of 7, that gives you 14, right? It gives you minus 14, of course, but minus times minus gives you plus. When you do the logarithmic value, it turns into plus 14. Okay? Yes?
The class is over at 12:30, and you said we should remind the 10 minutes before 5.
Okay. I'm going to stop here, okay? Because you have